Hello and welcome. Today I'll be going over the qualitative organic tests for different functional groups that you've learnt about in your organic chemistry modules. So let's start off with one of the first functional groups you looked at, alkenes, and this is something that you've definitely seen before. So the test is to add bromine water and shake, and what happens is you get this orange decolorization, this orange colorless color change. This happens as the bromine's used up. Bromine is orange. Bromine is added electrophilically across the double bond. So an electrophilic addition, which you've seen in your alkenes module. Here's the mechanism. It's always nice to remember these. So you have the nucleophilic attack on the bromine, electrons pushed towards the electron sink, formation of the bromonium ion intermediate, then the bromide attacking in to give you your products, your antidiols in this case. There is another test. This is to add potassium permanganate or potassium manganate 7, but I'm going to stick with permanganate. And if we look at the oxidation state here, we have oxygens. There's 4 of them in the -2, so that's -8. Potassium is +1, which means manganese is in the +7 oxidation state, so it's very oxidized. So what we see is this deep purple to color change. Deep purple is from the permanganates, that's the color of it. And then this is what happens. This is called oxidative cleavage to give ketones and carboxylic acids. You don't get aldehydes, as potassium permanganate is a very strong oxidizing agent, so it will oxidize alcohols, aldehydes straight to the carboxylic acids. So why does this color change happen? Well, the Mn7 plus is being reduced. You should know that transition metals create different complexes of different colors, depending on their oxidation state is one factor. And here are the colors of different various oxidation states. So we can see it gets reduced all the way from 7 plus to 2 plus. And there's where I found those colors. So next we have the test for alcohols and phenols. So we'll start off primary and secondary alcohols. You've seen this reaction before. It's to add potassium dichromate in sulfuric acid or acidified potassium dichromate. And we see this orange to green color change. Same reason as with permanganate, due to the oxidation state of the chromium. Here's some reaction schemes. So we have the primary alcohol going to the aldehyde and then getting further oxidized up to the carboxylic acid, and the secondary alcohol being oxidized to the ketone. For phenols, we instead add ferric chloride or iron 3 chloride, and what we see is a purple color. So moving on, we have halogenoalkanes, and you've learnt that halogenoalkanes undergo nucleophilic substitution reactions. So what we do is we perform one of those. We use aqueous sodium hydroxide in this mechanism. Here it is. And then we neutralize the excess base with nitric acid. I'll explain why we use this acid in a minute. And then we add silver nitrate. So we use nitric acid as what we form eventually is a precipitate of AgX. And so if we were to say use hydrochloric acid, we would get lots of AgCl, and thus we would mainly see the white precipitate even if we had a different halogen in there. So chlorines give white precipitate, bromides give cream precipitate, and the iodide gives a yellow precipitate, or primrose yellow precipitate. It's a particular shade. Next, we'll look at the iodoform test. This is a test for this methyl to carbonyl group. R can be alkyl or hydrogen. So this is performed with alkaline iodine, sodium hydroxide and iodine, which is made in situ, so in the situation. And what we see is a yellow precipitate and an antiseptic smell. So an example, we have acetone versus propanol. Acetone has this methyl group next to the carbonyl. Propanol does not, so we'll expect a positive result from acetone and a negative result from propanol. Next is going to be carbonyls, and that's going to be to add 2,4-DNP, 2,4-dinitrophenylhydrazine, or Brady's reagent. This reacts with carbonyls, so aldehydes and ketones, to give orange-yellow precipitates. And these products are 2,4-dinitrophenyl hydrozones. So here's the reaction scheme. So the way we would name these products is we put the carbonyl first. So for example, with ethanol, it would be ethanol 2,4-dinitrophenyl hydrazone. Just as something interesting. So then aldehydes, there's two tests for these. You've seen these before in your carbonyls module. The first is to use Toland's reagent, which is a solution made up of silver nitrate, ammonia, and sodium hydroxide. This is made again in situ, so in the situation. This reacts with aldehydes to give the carboxylate anion, as we're in base and solid silver, metal silver. And what we see is a silver mirror form. So here is the reaction scheme. You can see this is the reduction of this silver complex down to silver solid, and the oxidation of the aldehyde up to the carboxylic acid. Next then will be the Feynman's test, a solution made up of copper 2 sulfate and potassium sodium tartrate, which are stable on their own, not together, and thus again in situ. These are normally labelled Feynman's 1 and Feynman's 2. So what we see is this blue solution of copper 2 plus, and that goes to a brick red precipitate of copper 1 oxide. Here is the reaction scheme. Again, we can see reduction from 2 plus to 1 plus as the aldehyde gets oxidized. Next will be carboxylic acids, one that you've definitely seen before. That's to add sodium bicarbonate, and we'll see effervescence or fizzing, and then we can bubble that fizzing into lime water, which will turn the lime water milky, as the fizzing is carbon dioxide gas. So here is the full balanced equation. You should be able to see where everything comes from. So we get the salt, as this is an acid-base reaction. So next, in the next video, I'm going to discuss how we can use these tests to distinguish between a wide variety of compounds. So, thank you for watching.